Okay, I think we should be good to be live right now. Let's see, that is looking fine. Let's have a look over here. That is looking fine. Okay. I think we are all good to go, exactly on schedule. So, welcome once more to another live stream for the AP Calculus AB free response questions. This time we will be going over the 2022 questions for this exam. Last time we went over the 2011, so we're skipping a few years here just to get to another one we haven't gone over yet. But as always, we'll be going through all 6 of the free response questions to this exam, going over each step and correcting it through. Last time we did make channel history of actually getting all 54 questions of them correctly. 54 points, that is, out of all that were available. And so because of that, we should be all ready to go for this next session here. Okay, so as always, like before, you can submit all your questions directly to the email at the labcoatmath@gmail.com, or you can send it also to the live chat where we can be answering any of those live. Okay, so we have the 6 problems to go through here. As always with the AP Calculus test, is that the first 2 questions are calculator acceptable, so we'll be sending that one through the my very trusty TI-83 Plus. But without further ado, we'll be getting on through this exam here. And for this, we have each of the problems. Again, they'll all be copied down onto the notebook here so that we can just refer back to it immediately. There usually isn't that much space for answers on these types of packets, so we do the best that we can in the meantime. Okay, so I think we are all good to go. So we'll get started on the first problem, and we'll continue forth in that manner. Okay, so as before, I'll be copying over the first problem here, and if we can make sure that the camera is well focused here. So this is going to be the 2022 AP Calculus AB free response questions. Okay, very good. All right, we're still working on the handwriting, but it'll come about on its own time. So question number 1 begins that we have the time from 5 a.m. to 10 a.m. The rate at which vehicles arrive at a certain toll plaza is given by the A of t being equal to 450 multiplied by the square root of sine of 0.62 times t, where t is the number of hours after 5 a.m. and A of t is measured in vehicles per hour. Okay, and then it then takes a special note here that traffic is flowing smoothly at 5 a.m. with no vehicles waiting in line. Okay, very good. So with that, we should be able to, let me just double check here. We are having that ready to go. Okay. So with that, we have question A here, which begins that we must first write, but do not evaluate. An integral expression that gives the total number of vehicles that arrive at the toll plaza from 6 a.m. at t is equal to 1 to 10 a.m. at t is equal to 5. All right. So we have our first question already listed out for us. So we need to give that integral expression for those two different time periods. Okay. So because it's going from 6 a.m. to 10 a.m., we have ourselves the time interval. Okay. And again, A of t is going to be the rate in vehicles per hour in which those cars arrive at that toll booth. Okay. So because of that, then we can go ahead and say that if we want to know the vehicles arriving is going to be equal to, now we have to make a definite integral with the time going from 1 to 5. So we're looking at that difference there of how many arrived within that time frame. And we just go with A of t in respect to time. And A of t being the rate in vehicles per hour, by taking the integral of the rate equation, we bring it back to simply the number of vehicles that entered from those time changes there. Okay, so for us, then we can simply substitute in for the rate equation at 450 multiplied by the square root of sine of 0.62 times t. All of that dt. So this here is going to be that integral expression for us. All right. So very simple for part A. I think that's just all that they were looking for, just so that we can have that on paper. Okay. But part B says then to find the average value of the rate, which is going to be in vehicles per hour, which vehicles arrive at the toll plaza from 6 a.m. to 10 a.m. Okay, so because now they are asking for the average value of a specific function, again, the rate. So again, this is once again, if you want to take a note here, that's average value of A of t that they're asking for. A of t, of course, being that rate equation that they started us out with. So because we are doing average value of the rate, this means that we need to turn this into the average value equation of 1 over b minus a, going from a to b for any sort of function that we are looking to take the average value for. Okay, a very simple recollection from something that should be memorized by our calculus students of the types of things that they're looking for. Okay, so because we have the average value already set up there, then we can set it equal to the equation of 1 over. So now the time difference is going to be 5 minus 1, as those were the exact time frames that we still know from the previous problem. And going from 1 to 5 in terms of the hours of A of t being the rate equation. So what we will plug into our calculators, it's 1 over 4, that is, 1 minus 5, and the 5 minus 1 at top there. So 1 over 4, but the limits are still 1 to 5 of the A of t expression, so it's 450 multiplied by the sine in the square root of 0.62 times t. Of course, now we are evaluating this for the variable of t. Okay, so with that, this will be sent straight into our calculator, and we should be able to end up with a very reasonable answer. So that's from our previous session there, but nonetheless though, so we keep that 1 over 4 coefficient waiting for us after we multiply it with the function integral. So again, we're using that operation to take integrals with this graphing calculator. So it's going to be 450 times the square root of the sine function of 0.62 times the variable of t. Okay, so that is all shown right there. We close off that square root after the fact, and then we tell it that this is going to be for the variable of t going from 1 to 5 on the interval for the limits of integration. So we let this guy run, and we will see what we can get after it spits out a lovely answer for us. Okay, so it gets us 375.537 if we round it to the third decimal place. So write that down. So that's going to be 375.537. Now this is in units again. They did tell us is in vehicles per hour. Of course, the idea being that if you take an average value of a function, so again, we're doing the average value work, that just means the same units will carry over. So because a of t was the function that we took the average value of, a of t that we told us was in vehicles per hour at the start of the question. So because of that, we get this exact answer on this question. Okay, so that will be part B, very straightforward. Okay. And let's copy down part C. It says here, it's asking, is the rate at which vehicles arrive at the toll plaza at 6 a.m. Let's see, at the time is equal to 1, increasing or decreasing. Okay, and we need to show the reasons for that. Okay, so we want to know the rate at which vehicles arrive. So that sounds like a of t already, right? But they're asking if a of t, that rate, is increasing or decreasing, right? Those keywords right there will tell us that this question is asking instead of just for a of t, because they're asking if that function is increasing or decreasing. That would mean if they're asking about the derivative of a of t again, is that going to be positive or negative, right? That translation must turn out in our minds if we're looking to solve for this properly, right? Because we're looking for an increase or decrease on this function already. So because of that, we then need to take the first derivative of a of t in respect to t, okay? But then what they also want to know is that it's not just for the generic, that's going to be at the t is equal to 1 mark, okay? So we could go about doing this derivative by hand and plugging it in, but that really isn't the case for us. They don't necessarily need to know a prime of t in itself. We just need to know a prime of 1, because that time is equal to 1 is being plugged right into the derivative equation. That little discrepancy is important to note because we simply just need to go ahead and plug this directly into the calculator, right? So if we can do, we can do the derivative function, right, of a of 1. Again, that will give us the, in terms of calculator, a prime of 1 for us. Okay? So what that means in our sense is that we get to go back to our calculator, and at least for what I have, we can go and take the, it should be number 8, yeah. So the derivative function on this calculator, which means we still plug in for the exact equation of a of t, which is 450 times the square root of sine of 0.62 times the variable of t. Okay. So we close off the square root after closing off the sine function. But now we will tell it that we are doing this for the variable of t, and now only for the value of 1, and not the interval, because we're taking a derivative and not an integral over an entire section. So we do get something sent out to us as 140.947. Okay, so a prime 1 is 148.947. Okay, so what that means for us then is that we get this in terms of the units as vehicles per hour squared, right? So this is the change in the rate in which the vehicles are entering into the toll plaza. And because it is positive, as we note right there, okay, that means that the rate at which vehicles arrive at the toll plaza at 6 a.m. is increasing. And we have our work to show for it in the meantime. Okay, so a little bit of just an understanding that is being asked for. Again, this is going to be an increase of a rate function, the rate function which already was given to us as a of t at the start of the problem. And taking this all the way down, understanding we just need to plug in the t is equal to 1 into the first derivative to see if that rate is increasing or decreasing. And because it was positive, we were increasing at that time. Very good. So let's get over to part D here. It says that a line forms whenever a of t is greater than or equal to 400. Okay. Then it says here the number of vehicles in line at the time t for a is between t to 4 is given by a new function n of t being equal to the integral from a to t of a of x minus 400. Now we're taking this dx. Okay. All right. And now they're mentioning where a is the time when a line first begins to form. Okay, so it says to the nearest whole number, find the greatest number of vehicles in line from a to 4 on that time interval. So the cutoff there. Okay, so we have our work cut out for us here. I think I might actually need to turn the page over if we run out of space here, but that should be no problem for us. Okay, so we need to find those number of vehicles which are going to be in line. Again, the line function given by n of t given right there. Okay, so because of that, we need to look at, again, so the candidates, okay, for the maximum, they're asking for an absolute maximum in terms of what is available. So that absolute maximum can be, at least for in our case, again, the endpoints, so a and t, and of course any local maximums for n of t, right? Which means we will then have to take its first derivative. But what we can actually note is that a is going to be no good, because if we did n of a for that the many cars in line for this, that means we take a limit going from a to a, as shown right there. Any limit taking doesn't matter what kind of function you have, thanks to some very fundamental rules of definite integrals, is that by starting and ending at the exact same limit would be equal to 0. So therefore, a is no good, and we just need to look at the last time of t and any local maximums for n of t. Okay. Speaking of which, if we were to take the derivative, so n prime of t, to look at any local maximums for our case, well, we get to use fundamental theorem right here, meaning that we take the actual function a of t, okay, and then the minus the 400 at the end of that. But then that also means we just subtract the 0 from the a, because a is simply going to be a number and not a variable in our case. Okay, so with that, we then need to see where a of t is equal to 400 to take a look at that timing right there. And so we do have our work cut out for us. Okay, so because of this, right, we then realize that we have ourselves the point where we need to find a itself such that we can run the actual integral for this problem. Okay, which the actual function is going to be greater than or equal to 400 in that case. Okay, so let's have a look here then. Is that if we're going to be equal to 400, that all that really means that we have to then take a graph to look at that timing that is available. So going back to it, we have our graphing function, And we can plug in for A of t immediately. So it's 450 times the square root of sine of 0.62 times t. Okay. Wait, sorry, we need to go back to x because we're graphing. It needs to be in terms of x and y. If I can make sure to put that in properly. So we have that inside of the square root. Okay. And then we need to subtract 400 as a result to make sure we can look at where we're crossing 0. Okay. Window-wise, I think we're good because we're only really going from 1 to 5. So I think we should be fine. Because again, we're looking for any sort of crossing of 0. And looks like we cross a few times right there. So let's go ahead and have a look here. So with the trace function, we can look at some zeros. Looks like we have some zeros. If we bring this all the way back. There you go. Okay. So left side of that curve. Go to the right side of that curve. And this first point that crosses 0 right there is given to us at 1.469. Yeah, that's how if we round it. So the possible t's that we can look for is 1.469. And the other one, if we bring it down from the other side here, so let's recalculate for another 0. Bring it down. Okay, left side of that, right side of that. And we have a look here. So this 0 now on this crossing, 3.598 if we round it. Okay. So 3.598. Okay, so both of them are within that limit that we're looking for. That is underneath 4. So I think we will have to turn this page over for a bit more space to work on. And we'll definitely be well on our way. Okay, so this is part D continued for this problem. Okay, so let me just make sure we copy over that exactly. So it's 469. Okay. So the t is equal to 1.469, and then also the 3.598. Yeah, those are both. Yep. Okay, so those two will then be our candidates for our possible absolute maximum. So all we need to do then is plug that right into these two parts right here. At least for us, again. If this starts at again, this is where the first time that A of t was greater than or equal to 400 at that time. So that is going to be time A for us. And then we get to move it all the way down into the end of the time where, again, once more, A of t was equal to 400 one more time as it goes underneath the axis. Okay. So with that, we can have ourselves a moment here. Let me double check here. Yeah, where the line begins to form. You're good. Okay. So let's have a look here. So n of the time being the latest one of 3.598. We can then take the integral. Again, the time where the line first forms. Again, this is the first forming of that line that they are talking about. And then t being the ending of it, 3.598 in that sense. Okay. And so because of that, we then get to take a look at this integral going from a of x minus 400 in terms of dx. Okay, so because of that, we then get to go and plug everything in here into the calculator at last of this integral 1.469 3.598 for the a of t equation. So 450 times the square root of sine of 0.62 times x. All this in terms of x for us. Okay, with the minus 400 first, and then dx like that. Okay, so the number of vehicles that are going to be in the line at this time, we can go ahead and take, in our sense, the function integral, what we're looking at right there. Okay, now it's going to be the a of x minus 400, so it's going to be 450 times the square root of sine of 0.62. We can go in terms of x this time because that's what the problem is asking for. We close that off, we subtract the 400, and we're taking this in the value of x to be evaluated from the two time frames of the 1.469 going all the way to 3.598. Just like that. Okay? So by submitting that through, we end up with 71.25 for the whole nearest whole number, so that would just be 71 vehicles in line. Okay. And that really will be the only contributing effect on this, because again, we took the graph of the derivative function. We only had two crossings, one at the start, which would have been 0, given that we're starting and ending on the same exact time point, and then the ending part, which was the only one that we could really have evaluated for. Okay, and then lastly, actually no, there's one more actually. We can then, so again, this was at the t being equal to 3.598. So we could do one more, where we can contribute. We can now compare. So compare 2 at the start, 1.469, and going all the way to the 4 at the very end of the time interval, which they're asking for. So we do the same exact integral as a comparison of an absolute maximum. So minus 400 on the outside dx. Did I do the minus 400? Yes, I did. Okay, just making sure. Okay, so we go redo the same exact problem. So this time, we just replace that last ending part. So again, the same exact a of t equation, 450 times the square root of sine of 0.62 times x minus the 400 on the outside. Now, still taking it in terms of x right there, but only ending at the interval of 4, so that's 62.338. And so rounded, that's going to be 62 vehicles in line. Again, this is going to be at the time is equal to 4 mark, so the ending of our evaluation there. Okay, so because of that, this is going to be the maximum amount. Okay, the greatest number of vehicles is the, all right, so now we can say the maximum number of vehicles in line is 71 at time t is equal to 3.598. Okay. And we have our work to show for it. We did compare at a local maximum that was possible from the first derivative graph, as well as the actual ending time frame, because again, the interval was beginning at the time where the line begins at A, all the way to the 4th hour. Of course, the time where the line starts, there's going to be no cars in line, so there's no point calculating for that one. But we have everything that we need on this side to prove for it. Very good. So that is going to be problem number 1. And we'll go over problem number 2, and then we'll begin our corrections as we go 2 at a time for this exam. Okay. So with this, we have problem number 2 to begin with over here. Okay. So I think this should still work out once I start writing some stuff. So we have ourselves a graph that I'm going to copy over first. So let's see, we get over from 1, 2, 1 right there, 1 right there, 1 right there. Okay, good. That focused up quite nicely. So we go with this line going up here. Sure, there's some intersection there. You bring this down and then bring it up like this. Okay, not the best, but it'll do for now. Okay, so we have our graph right there. Then context says that let f and g be the functions defined by the functions defined by f of x being equal to the natural log of x plus 3 and g of x being equal to x to the 4th plus 2x to the 3rd. Okay, so then the graphs of f and g shown in the figure above intersect at x is equal to -2 and x is equal to b, where b must be greater than 0. Okay, a very interesting prospect for us right here. with all of this information. But let's go over to part A here to begin to see what they really want for us to do. It says here that for -2 being in between x all the way to b, let h of x, so now a new function, be the vertical distance between the graphs of f and g. Now they're asking, is h increasing or decreasing at x is equal to -0.5. Okay? And we need, of course, the reasoning behind it. All right, very nice. So we want to take a look here again. So we have h of x, a function, again, the vertical distance between f and g. And then they want to know if that h is increasing or decreasing. So we have a few things to point out here. First off is that we then need to know which of these graphs is really which, because they don't tell us, right, for f and g. So they give us the equations, f being the natural log of x plus 3, and g of x being equal to x to the fourth plus 2x to the third. So given that this is problem number 2, this is still the calculator section. If you really were in doubt, a student could very easily just graph it straight onto the calculator. So let's go have a look first, just to make sure we're not losing our minds here, that if we took the natural log of x plus 3 on this side, right? And then if they want to take a look, making sure our window is set, let's go to -3 all the way to +2, just to show properly on that. Okay, so if you were to graph that, we end up with this kind of a function with that curl coming across, again, near the x, that y is equal to 1 spot, again, in a straight line. So that does match with the top function. That should be f of x, and by deduction, g of x should be that bottom function. Okay. For those that still aren't very convinced as to find which equation is going to be which, if they gave you the arbitrary graph like that, and we can take a look at the differences between the two. Being a natural log function, there shouldn't be many curls to it. Again, you see one curl is kind of up and down on its own. The natural log is a nice, very, at least in this case, a nice curved function, which continues going along in its form of an increasing function. While x to the fourth plus 2x to the third, again, this has the exponents of x to the fourth and x to the third, meaning we will get some nice curls along there, which should match our deduction. Okay, so now that we've got that out of the way, then we can show that h of x, in this case, again, as I said, is the vertical distance between f and g. Well, vertical distance is measured in the results of those functions. So if you want to find that distance, all that we need to do is just say that it is a top function, f of x, minus the bottom function, g of x. And it should be really easily deduced like that. Okay? So alongside that, but that's not what they're asking for. They're asking to see if it's increasing or decreasing at a specific x value. Which then means if it's increasing or decreasing, we need to go ahead and take the first derivative of that function, which thanks to some nice addition rule, just means we are taking the derivatives of that whole subtraction. Okay? So in our case though, all we need to do then is that we can go ahead and plug in for h prime as 0.5. Given that those derivatives means that we have to just take the natural log of x plus 3 subtracted by x to the fourth minus 2x to the third. With that subtraction, just taking that derivative straight away into our calculator, as we don't need to do this by hand, given that this is a calculator section problem. Okay, so we can very easily do that right on our calculators, as we have ourselves the function derivative operation on this calculator. So again, it's going to be the natural log. So we take the natural log of x plus 3. So that is the function of f. We subtract it now with all of the g function, which would be x to the fourth plus 2 times x to the third power. Okay. So all of that is going to be subtracted. Make sure the parentheses line up there. And we're taking this for the variable of x at the value of -0.5. Okay. So of course, being able to put that into the calculator properly is going to be a skill which many students still need to practice. But nonetheless, though, we have everything we need to then realize that we end up with, if we go do a bit of rounding, is going to be -0.6 in our case. Okay. So because we have a negative value, in terms of the derivative of that function, that means that we are going to be decreasing, right? So the distance between f and g, again known as h of x, is decreasing at the value of x is equal to negative 0.5. And our work will show for it with our conclusion there, what we are looking for. Okay, should be pretty straightforward with a little bit of understanding of what that looks like for this type of question. Okay, so very interesting that I actually wrote this in the opposite direction, but that's fine. We can just solve this around. So actually, a little bit of a typo. I answered question B first, but nonetheless, it shouldn't really make much of a difference. We're going to go back to part A anyways and answer it as such. So then it says for us to find the area of the region enclosed by graphs F and G. Okay, so an area question, very easy. We've already found ourselves which one was the top and bottom function, right? So again, if this is the entire area between F and G, all that really means is that if we want to find an area between multiple graphs, which I have very conveniently made a video about on our main channel, but in any case, area is going to be between those two values. We need to find those bounds in which they intersect, but as always, it's going to be the top function minus the bottom function. Okay, and we can go dx because by taking vertical sections we're just fine, coming across it very easily. So in our case, we need to then find those limits at which those two intersect. Okay, we can do that very easily, and we can do either by setting them equal to each other, or in our case, we can actually go ahead and graph both of those functions, because this is question number 2, still a graphing calculator section. So we just go x to the 4th plus 2 times x to the 3rd power. So because of that, we can go ahead and graph both functions, as you can see, very nicely reflected, with the shapes of that matching the shape of what we started with as part of the graph that was given to us. So we can go ahead and trace in some intersections of both curves. Let's go to the one on the left first. That one's a lot easier for me. So first curve, second curve, and we take a note. So this first intersection right there, it just graphed as x is equal to negative 2 and y is equal to 0, just to make sure. So intersections as we state right there. Again, we have our first point at negative 2 comma 0, as what the calculator said. And now let's go to that second intersection, the one all the way on that side. So let's go grab that intersection going all the way across for the first curve, the one right there. We want to get close to it on that natural log curve right there. And the second one is just right there. It can then calculate for it. I'll give you a second. So that second intersection, all on the right side, has those coordinates. So x being 0.782 rounded, comma 1.330. Okay, very good. So we have the two intersections listed out right there. And so because of that, we have exactly those limits in which we will start and finish our integration as such, going from negative 2 all the way to positive 0.782, just like that. And again, it's the top minus bottom function, again, top being the f of x and bottom being g of x, as we have shown in our work earlier. Right, so because of that, f of x is going to be the natural log of x plus 3, all subtracted by the x to the 4th plus 2x to the 3rd in terms of x. Okay, very easily set up there. So this will all be then thrown right into our calculator. So then the area that is calculated between the two is going to be nicely inputted straight away into our section right here of the function integral. So keep in mind, we start first with that natural log of x plus 3, subtracted all by x to the 4th power plus 2 times x to the 3rd power. Okay. So all of that now is very easily inputted. We're doing this in terms of the variable of x going from the limits of negative 2 all the way up to 0.782. So it runs through and it gives us the area of 3.604 if we round it to the decimal place. So 3.604 is going to be the area in between those two curves. A very simple exercise for those who do understand that area being the top minus bottom function with all the practice that we've done so far. And we just get a very simple area after discovering where those points of intersection truly are. Okay, let's go over to part C here. So that it says that the region enclosed by the graphs of F and G is the base of a solid. Okay, then it continues that the cross sections of the solid taken that are perpendicular to the x-axis are squares. Okay, then it says find the volume of the solid. Very nice. Okay, so we've got everything we need over here. Again, so now they're asking for another volume question, knowing that if we were to take the mental note that if it's a volume in terms of squares for us, that just means that we take that same integral going to a to b for that region, we'll call it r. Again, but now we have to take the entire thing and square it before the integral. Again, meaning that we take the square of the function going in both directions, the x and the y, and then integrating all the way across, adding it all up to a total volume. Okay. So because of that, this is going to be the way that we set up this problem. Of course, the region now, again, is going to be the same region that we've calculated before, f of x minus g of x in that fashion. So because of that, we can then find ourselves that volume. The limits stay exactly the same as part A, 0.782 being the ending part where those two intersect. And we will go with the now f of x minus g of x, which is the natural log of x plus 3, subtracted by all of x to the fourth plus 2x to the third power. Now, all of this needs to be squared dx, right? So again, this was the makeup of that region that we were discussing, that is in between f and g. So after subtracting, we then square the entirety of that difference so that we can end up with a volume that we can calculate for. Okay, so by putting that all together, this will be stuck right into our calculators very nicely. So we go back once more into the function integral operation again, and we go and take this for we start with that parentheses because we will square it afterwards. So the natural log of x plus 3 subtracted by, once more, x to the fourth power plus 2 times x to the third power, third power right there. Okay, so that subtraction is first going to happen, and then we close it off such that all of this will then can be raised to the second power again. Okay, so again, by squaring that, we are then going into an area, into a volume question. Still, we're telling the calculator that we're doing this in terms of x, and our limit's going from -2 to 0.782 as calculated earlier in this problem. Okay, so everything looks like it should match. We start squaring, again, squaring into an area, integrating into a volume, and that is the volume that we end up with, 5.340, as shown as the volume. Okay. A very simple exercise for us to recall the actual volume of a square, volume of a solid with cross sections of squares for us to then plug right into. Okay. With this being bigger than the area, that does make sense. We're increasing by another dimension. So that does check out mentally on our side as something that we can be confident is going to be correct. All right, let's get lastly into problem D here, and then we can start correcting. So it says here that a vertical line, that's isovertical, AL, vertical line in the XY plane travels from left to right along the base of the solid that is in part C. Okay, let's see, very interesting. So this is the vertical line is moving at a constant rate of 7 units per second. Okay. Then it says find the rate of change of the area of the cross section above the vertical line with respect to time when the vertical line is at position x is equal to negative 0.5. All right, this is quite the banger of a problem if I do say so myself. Okay, so let's actually illustrate what's happening here just so that we're all on the same page. Let me swap over to a nice, this green color might not stand up very well. Let me get to my very trusty light blue pen over here. So we have ourselves a vertical line now that's slashing right in between those two functions. And we're moving to the right. So this line is, again, it's coming all the way across that function. And it's going at a rate of 7 units per second. Okay. So this guy is coming all the way across and it's basically slicing it up as we move along this guy. Okay. So again, they want to know at x is equal to negative 0.5. We need to see what the change in the cross section is going to be. Okay. In respect to time. All right, so we're slicing up that function and that area going all the way across, and we need to then see the change in the area per second with that vertical line at a very specific position. So this is quite nice because if we're going to find that area of any sort of cross section between the two functions, we need to start with that, right? So the area of that square. Again, everything was already described in part C. So if we're just going with the area, not for a total volume, the area was just simply going to be that difference of f minus g of x. Again, this is the entire region, right? This being the region that was already described in the start of the graph. And so by squaring it, that's going to be the area of the square. We just need to plug in for very specific x values because of that. Okay. So with that, right, we have the area at any given time, but we're not looking for just area. We need to look at it in terms of area with change in respect to time. Okay, so because of that, we can then go ahead and start putting it in straight away, right? Given that we have ourselves here, right, we are looking for the change, again, in area in respect to time, dx over dt, as shown right there. Okay, again, this is going to be, right, the derivative respect to time. Okay, so that is meant to be our main goal right here. Okay, so not only just be a fixed area, we need to do it changing in respect to time by taking that first derivative of this kind of equation. Okay, which means, yes, we will need to do ourselves a favor in doing implicit differentiation in order to find this exact part right here. Okay, so I think, yeah, if we start off by doing it by hand, that might be the best option so far. I'm trying to think about this because we're supposed to be doing this in terms of the a calculator problem. So let's give this a little bit more thought right before we start jumping into some conclusions here. Let's see. Yeah, so by moving, we are just simply coming across from the left to the right for this type of problem. Yeah, so what I'm trying to think about here is that we can actually leave everything in terms of this type of problem. So the idea being that if we actually move this first to in the generic sense of the two functions, so what I personally like to do is if we FOIL this out as if they were in the generic state, we can then go ahead and take the derivative in respect to time, as what they were asking for is that, again, this area over time in which they were looking to find this problem to be in. So if we went ahead and this one actually would require a little bit of product rule here, so let's go about doing that. But that's two different functions though. That doesn't play very nicely with what we have. But okay, so maybe not like that. So let's actually flip this right over. We're actually out of space here, and this one does seem a little bit of a odd section right here. This doesn't seem like it. If we really just did the area function, so again, area between the two, again, as if we want to recall that, again, that's the area of that square that's above each of them. Again, the calculator is able to do the derivative, but not in terms of implicit, just in terms of just the x value. So I'm trying to see here where that 7 units per second comes into play, because they gave that to us for a reason. Usually don't try to give us these random facts for no reason. The idea being that if we just did the derivative in terms of x, that's what we're doing on that side. Again, evaluated at x being equal to negative 0.5. But we need to then do it, we need to do this in terms of t though. It needs to be area per second. Okay. I'm not really coming to anything right now, but let me see here. If we just ran this through just to take a quick look at it, if we were to take the derivative of that difference there, of all of the natural log of x plus 3, subtracting it with the x to the 4th plus 2 x to the 3rd power, so all this squared, and then we did this in terms of x at negative 0.5. All right, so again, we're getting a change in area, but we're not getting this in terms of per seconds. This is supposed to be I'm trying to think about this because this doesn't seem to add up very well in my head at this moment. Just bear with that in just a second here. I wouldn't say that this really puts it through there. Yeah, okay. Okay, I thought as much. That was indeed going to be the way that they want us to solve it, if that were the case. Yeah, because the units didn't match up for me. So this indeed is trying to say that if we took a step back here, what I'm trying to figure out right now is that if we did the derivative of area in terms of x, that's what we're doing first, if we took the derivative of the area function. But then the issue is that they gave us instead, because this has nothing to do with time, right? So again, doing this kind of derivative has nothing to do with time. Right? We are just simply taking the rate of change of the area, but we still need to go and bring in the time factor because the units at our end here need to be the area per second. That's what they want us to do, right? Okay. So idea being here that if we then took a derivative in terms of the area over dx, again, this will just give us, this brings back a dimension, right? Again, if integrals give us 1 up on the dimension from area into volume, we are going back to just simply the units in the first dimension. But then if we multiply it with the units per second in terms of the speed in which that line is moving, again, across the axis, that makes it back to the units that we want, units squared per second, as was the purpose of this question right here. Okay, so yes, that does make the most sense to me at this time. So let's go about doing that. So still, I think our line of work here still makes sense, at least what we did so far with the derivative. So we took the derivative of the area in terms of x, so it became negative 1.325. Again, this is going to be just singular units here because we took the derivative in respect to the x. And so by multiplying this by the 7 units per second, we then come across the fact that by putting that through will be negative 9.272 units squared per second. And that will be the change in area per second. Okay? So this takes just a little bit of understanding as to how these units will work out. So again, we're a little bit hung up on the fact that this is the area. Again, the area function, if we took the derivative, we are moving back a unit. So now again, area, if we want to make sure we're on the same page here, area, the area function of the fx minus g of x to the second power for each of those squares, that is going to be in units squared right there. Okay. The main issue though is that if we then took that function and took its derivative in respect to x, then by putting the x once more in the denominator, that just makes it units to the first power by taking that derivative. But understanding, let's go. Okay, looks like there were some issues with the stream. Okay, I think we should be back now. Yes, there were some mix-ups with that. Okay, I think we're fine now. There's a little bit. Okay, I think we should be good. Everything else is looking good back on my end. Yeah, I think we're back. Okay, sorry about that. I don't know. There's some weird things happening with the connection here. What is this? Okay. Yeah, we might have to give this a minute here. Normally this wouldn't have happened otherwise. But let's just make sure. Are we fine here? I think we're fine now. A little bit of technical difficulties, but I think we should be fine. Yeah. Okay. I know there might be a little bit of hit to the quality, but I think we should be still good for this as we move through. Okay. So, just as a quick recap, since we got a little bit of a buffer there, is that, again, we still, the question was asking if we really did understand what it means to keep the units in line for this type of problem. Okay? So, with this, again, this is going to be if we took the area's derivative in respect to x, that means we actually go back and we go back to the first dimension for this type of problem. Again, the problem asked for units in terms of the squared units, so the area per second change, right? So because there's still no time value in terms of taking the derivative in respect to x, we simply needed to multiply the derivative with the rate at which the line moved, giving us back to the units squared per second that they were asking for. Took a little bit just to make sure we were all on the same page there, but I think we are good for it as we move forward here. Okay, so that was all 4 parts to these first 2 questions. So let's quickly get back to the first problem and let's see how well we've scored so far. Okay. So starting with this, we'll get our correcting pen here. And just to get everything set up properly, and with this example packet here, I usually like to list off all 6 questions because that's how many questions there are in this packet, and see how many total points that we have scored so far is out of 54. Again, keep in mind is something to note is that this type of exam is not graded out of just the raw percentage. Everything is curved to the national average, so it is going to be just really based on how well you score in reference to everybody else. But in any case though, let's get to some corrections and let's see what we're looking at. This is going to be a little bit different the way that they do the scoring guidelines now. Let me see if I can swap it over for just a second here. Right, so this is what I'll be looking at when I do my corrections, is that we have our each question here. Again, starting with question number 1, they'll give you the way that you can score the points across each of these, and I will mark that as such for this packet. Okay, so with that, let's go swap it back over into the actual answers that we have here, and let's see to it what we have. Okay, so with question number 1, we have ourselves this first part. So question A, again, they wanted us to set the right but do not evaluate that integral expression for the number of cars that entered from the 1 to 5 time frame for this, which again, well, we need to see the actual amounts, right? So going from 1 to 5 of the A of t, again, that was exactly what they wanted to see. So that's 1 out of 1 correct. And it's 1 to 5 for the A of t function substituted in. Okay. Then they'll note as we go to part B here. So if we're going to find the average value for this, and we set it up as the 1 over 1 minus 5 of that A of t, that exact function that we were looking to take the average value for. And so by doing that, we just plug everything straight in and we get 375.537. We can round it off to the 3-digit place, which is fine. So you both get 1 point. We get 1 point for showing that we know how to do average value as a simple equation. And then we get the actual answer in vehicles per hour. And that would be both points given to us for this part. Okay. Then moving onwards to part C, and they wanted to see the rate at which those vehicles will arrive, and now exactly at the 6 a.m. mark, and was that increasing or decreasing for that rate. So yes, we do need to set up that we need to do a prime of 1 as the derivative function, again, to see the rate of change of the rate. So because of that, we showing that we need to do a prime of 1 as the actual positive or negative value to give us our conclusion is correct. And of course, the answer showing that we end up with a positive 148.947 does show that the rate at which those cars are entering is going to be increasing at that time frame. So that is once more 2 out of 2 correct for this part. And lastly, in part D here, where we need to find those maximums at which the number of the line, so again, this is the line equation that they wanted us to see. So of course, we then showing that we have n prime of t being set to be equal to 0. That's exactly what they wanted to see, that we understand fundamental theorem of calculus, how to take the derivative of an integral. And now, yep, so at the time points, the way that they cross the x-axis, again, at the graph, again, this was done on the graphing calculator, right? That was going to be another point for them to show that we understood what we're doing there, right? To find those possible maximums. And then lastly, we show the values of 62 and 71 as we plug in those values into the definite integral that they were looking for. And so the maximum number of cars is going to be at 3.597 value mark. Okay, so that 71 was indeed the actual answer they're looking for. Okay, so because of this is going to be all 4 out of 4 correct for that part, giving us our grand total of 9 points for question number 1 being good. Okay, so with that, everything was exactly in line the way that they should be for question number 1. All right, so then moving on to question number 2 here is that if we want to start, this was part A, again, we did a little bit out of order, but we can grade it just on the right one. So area enclosed, again, was going to be the top minus bottom. So we needed to show, again, where that intersection was going to be, right? So at the 0.782 was going to be correct. We set up the integral accordingly of the f of x minus g of x that they were looking for to know how to find the area enclosed between those two functions. And so the limits was indeed correct at our intersection evaluation on our graphing calculator, and the area of 3.604 was indeed correct. So that's theoretically correct for this part. Okay, then going over to part B, which we have up here that we answered first here, right? They want, if we were doing the vertical distance and the decreasing factor, again, we needed to show that we were dealing with h prime of 0.5, as shown there, again, shown as f prime of x minus g prime of x, as such. Okay, and because of that, that will give us what they're looking for, again, of how we understand we can show that it is increasing or decreasing in that rate of change of that height between those two functions. And then by plugging that right into the calculator, us getting the negative 0.6 was indeed going to be the correct answer. So us concluding that the distance is decreasing because of the first derivative being negative is enough for us to get 2 out of 2 correct for part B. All right, moving down over to part C, we have ourselves the question about, again, the cross sections being perpendicular to the x-axis, being squares, and we need to find the volume of the solid that results from that. So we do set up the integral going that we have to square that difference in the region. Again, bringing it up to the second dimension, taking the integral, bringing it to the third dimension. So our integrand is going to be set up properly, again, at the points where those two functions intersected. The difference between f and g, all raised to the second power, was exactly what they wanted to see in terms of the way the integrand will be set up. And our answer of a volume of 5.340 is going to be correct, giving us 2 out of 2 correct again for part C. Okay. Lastly here, part D was the challenging one. Again, that was for us to understand how to do the difference in area in respect to time, right? That was something that they gave us. Again, in terms of the actual rate at which that line, again, we had that line moving across, and we need to see what that area, the area of that cross section is changing with that line moving 7 units per second over to the right side. So with that, we move to the back because we ran out of space here. But again, our area equation, again, was already given as the f minus g, all of that squared. But we need to go take the derivative of that because we need to see the change in the area. So that's a d over dx part. Again, we took the derivative in respect to x while waiting for us with the 7 units per second. That's what the line was moving, given, again, in that same direction that they were talking about at the start of the problem. And we have to take the derivative of that, multiply with the 7 units per second. And by doing that, we can plug that straight away through the calculator. With the derivative in respect to x at that point. Then we just took that answer of the negative 1.325 that calculator gave us, multiplied by the 7 units per second, and we end up with the negative 9.272. That answer was indeed what they're looking for as a change of area as that line moved from the left side over to the right side across that entire solid. Okay, so with that, this will give us all the 2 out of 2 points that we need, showing how we understand how to do the change of area in respect to time with that line moving with that little piece of information they gave us. So without anything of them deeming this incorrect, both questions 1 and 2 will be 9 out of 9 correct. Okay, we are once more well on our way, hopefully, to see if we can get our second section together of these free response questions to be done all perfectly, as we can continue our streak since how well we did on that last time. Okay, so with that, we can go ahead and move on to questions number 3 and 4. Because of that, something to note, of course, is that with questions 3 all the way to 6, so the rest of this exam is not going to need a calculator. So we'll go throw this off to the side and get to the second part of this exam. Hopefully everything was explained precisely. Again, as always, all questions that students might have can be sent directly to the labcodemath@gmail.com email over there at the left side, or any other questions sent directly to the chat will be answered as well. Okay, so because of this, let's get on to question number 3, and let's copy over another graph in which they have so graciously given to us. So let's have a look here. Have the graph like this. We go vertical 2 times, we go underneath 2 times here, then we go across 7, 1, 2, 3, 4, 5, 6, 7, like this. Okay. And going up to 4 with a lower radius of 2, so we have a semicircle right here. I can graph that properly. We go up to 6, 2 up there in a straight line, and go to 7, 1 down there. 7, 1, 6, 2 as points right there. Something to note that this is the graph of f prime. Okay. Something some students might miss if they're not paying attention, but we definitely caught note of that. Context-wise, they're saying that we need to let f be a differentiable function. Differentiable function with f of 4 being equal to 3 on the interval 0 going to x to 7. The graph of f prime, the derivative of f, then consists of a semicircle and 2 line segments. Okay, very good that they've explicitly stated that for us, something we can keep track of as we move into the next question. All right, part A is very simple. They just want to find the actual points, f of 0 and f of 5. Okay, very good. Wow, this looks like something that is going to need us to use the fundamental theorem of calculus immediately, because we only have the derivative function to work off of, and one initial point of 4, 3. Very helpful for them to give that to us. Of course, fundamental theorem showing that if we then take the first derivative integral, so again the f prime of x, which is given to us on the graph, then if we had that evaluated from 0 to positive 4, that would mean, using fundamental theorem, we can actually isolate the 2 differences of those points of f of 4 minus f of 0. Okay? Very nice, but of course, because we need to find f of 0, we just need to move across f of 0 on the other side over there, meaning that f of 0 isolated is going to be the actual f of 4 point, now subtracted with that integral 0 to 4 f prime of x dx. Okay. Something to note, of course, is that this is going to be given to us as 3 from the beginning of the problem, while that integral is going to be then found by area under the curve, as shown with the definite integral of that graph given right there. Okay, so because of that, we can then set everything up here, f of 0 being equal to 3. Now, with the area going from 0 to 4, as shown on that definite integral, we need to go all the way across the entire semicircle, as 4, 0 was indeed the ending of that semicircle itself. Okay? So if we want to subtract from an area of a semicircle, right, remember that semicircle itself is going to have an area of pi over 2 times r squared, right? Again, normally pi r squared is going to be the area of a full circle, but if we are going to cut that exactly in half, we just make sure we have that coefficient of 1/2 waiting for us on the outside of that. A radius, of course, for this type of circle, again, just keep everything simple. If this is going to be the center point and we're reaching all the end, the radius of this circle is going to be 2, right, from the center to any edge. So because of that, we get pi over 2 times 2 squared waiting for us as the area of that semicircle. So let's get to some work here. Again, 2 squared being 4, we can cancel that out, making a whole 2 at the end. So this makes it 3 minus 2 pi as a result of f of 0. Okay, that's our first response given there. And we can find, knowing that if we swap this around, because we're going at f of 5 here, is that if we can rearrange the limits going from 4 to 5 to contain 4, which is still our known point of the original function, that we can then take the 4 to 5 definite integral of the first derivative of f, meaning that, again, according to fundamental theorem of calculus, something that all students should be able to follow along with, is that we end up with the points f of 5 minus f of 4 as that result. With us knowing f of 4, we can move that over algebraically to the other side. And so we can isolate f of 5 being now the integral going from 4 to 5 for this function, f prime of x given on the graph, added with f of 4 waiting on the other side. F of 4 was already given as 3, again, at the start of the problem. While this needs to, again, once again, be an area under the graph. Yep. From 4 to 5, though, is that 4 to 5 is going to be just this nice little section of a triangle waiting for us between those 2 points. Again, the circle ends at 4. We just need to go one more over to the right to get it to 5 between those limits. So because of that, again, all we do have, though, is that we don't exactly know where 5 is going to lie on, except for the fact that because we have our points 4, 0, and 4, 0 is going to be a straight line going up to 6, 2. And very simple deduction. We could do the actual equation itself, but again, we can show that 5, 1 will be in between those two straight line points right there. Okay, so because of that, right, the area will then be, in this case, a triangle. Remember, we had triangle underneath that straight line right there. So with the triangle being underneath those two, that just means that we can set up the f of 5 equation as the area of 1/2, the base of 1, the height of 1, and 5, 1 being the height of that actual point itself, and then adding it with a 3 on the other side. So 1/2 plus the 3, we can leave it as the mixed number of 3.5, or we can call it 7/2. Either case wouldn't be the matter for f of 5, as our work all cuts out the same for us. Okay, just a few steps just to make sure we're all on the same page as to understanding how fundamental theorem of calculus will work, but we should be all the better for it. Okay. Then for part B, it says here that we need to find the x coordinates of all points of inflection on the graph of f from 0 all the way to 0 to 7 for the x value. Okay? And we obviously need to show all the work for it. Okay, points of inflection of the graph of f. That does sound quite intriguing, as points of inflection would then imply that we need to go take the second derivative of x, right? Again, and we need to look for that change of going from negative into a positive, or a positive into a negative sign for that second derivative. Okay, meaning that if we're going for second derivative and change of those signs, we can go ahead and look at the first derivative graph, because that's all that they've given us so far, right? So if the second derivative is changing signs from positive to negative or negative to positive, again, in terms of translation, this means that for the first derivative graph, right, we need to look at change in increase to decrease, or again, that change again in the other way, in decrease changing into an increase on that first derivative graph, right? We can look at analytically again. As we can see, we have some changes here, right? Again, so if the first derivative is decreasing and then increasing, as you can see, at exactly the point in which that circle reaches its pinnacle right there, that arc. So again, decreasing into an increase, that is a possible point of inflection. So again, at x is equal to +1, there could be one right there. Again, an increase, a decrease into an increase for the graph of f prime. So we can note here is that at x is equal to 1, we were decreasing first, and then we're increasing after that fact. Then, as we're increasing up to 1, right, we pause right there, and then we keep increasing some more at the x is equal to 4 mark. So that's going to be well on its own. But when we reach to x is equal to 6 there, we see we climb, we're increasing on the first derivative, and then we dip back down on that point afterwards. So at 6 and beyond 6 to 7, we are decreasing again on that first derivative, meaning that second derivative has the signs of negative to positive, then positive after 4, then back down to negative after 6. So it looks like we have two potential candidates for points of inflection, right? So the points of inflection for f are on x is equal to 1 and x is equal to 6, right? Our work showing for itself is, again, if we change the increase to decrease or decrease to increase as shown on the parts of f prime, that would mean that we're changing the inflection or that curvature of the original f graph. Okay, so that should work out pretty well. Then let's get to part C here, that it's going to say let g be the function defined by g of x being equal to f of x on what intervals if any is g decreasing for 0 going to x to 7. Okay. And we need to show the work. All right, very good. So we have I didn't write that properly. Not g of x equal to, so sorry, let's try that again. The idea being that g of x is equal to f of x minus x. That's going to be the relationship between the two. Okay. So now they want to know where it's still that g is decreasing along that interval. Okay. Decreasing, of course, means that we then need to take the first derivative and want to see if it's less than 0, as that mathematically proves that that function is decreasing. So because of that, the first derivative of g is going to be given as f prime of x minus 1, as the first derivative will dictate. Then, because of that, we need to set this guy equal to 0 to see what that looks like on the number line for us to analyze that properly. Okay. So if g prime is really f prime of x minus 1, then all we really need to do is look at all the points in which that is not the case, right? Because if this is going to be the graph, right, that means if f prime of x is less than positive 1, right, and if we're underneath that, that means we're going to be all negative numbers there, right? So then g prime of x is less than 0 on that sense. Okay, so because of, let's see where all the points where that's true, which is going to be up to the case at the 5,1 point that we found earlier, up to there. So everything below that is going to be underneath the axis, and then 7,1 is the end point right there, so it doesn't get any lower than that. So the interval at which the g of x is decreasing across that, again, is now going to be very easily shown that everything that, so g of x is decreasing on the interval. Now again, because we are looking for everything underneath the f prime x being equal to 1, because of the relationship that we discovered right there, okay, we can then definitively say that going from the interval 0 all the way to positive 5, okay, for x, that is going to be underneath the g prime being less than or equal to 0. Because of that, again, all of this being underneath the axis all the way up to that positive 1 point, as shown with our relationship between f prime and g prime right there from our derivative. Okay. That was pretty straightforward. Then let's go ahead and see then that for the function g in part C, okay, it then says find the absolute minimum value on the interval 0 going all the way to 7 for the x. Okay, absolute minimum. So we've got another one of these guys walking right up to us. The absolute minimum would then mean that we need to look at all the candidates that are possible for this type of reality for us, meaning that for the x values, and we need to compare it with the g of x values as well to see which one really is the smallest amongst all the candidates. which would include the endpoints of 0 and 7, as well as the other times in which g prime of x, again, is any local minimums as well, right? Which again needs to be where g prime of x is equal to 0, right? We need to see some points in which that is going to be the case, which we do have two of them. Again, if g prime of x equal to 0, that meant that the f prime of x must be equal to positive 1, as the relationship in part C did describe. So because of that, we have 2 points, 5 and 7. 7 we already have listed down, so we don't need to repeat that again. But if x is equal to 5, that is going to be another possibility for us to test out. Okay, so now we have to start plugging each of those points to take a look and list out those values for us to consider. So g of 0 in this sense is going to be f of 0 minus 0, because again f of the g of x is defined as f of x minus x, so that all falls into place. F of 0 we've already found in part A quite nicely as the 3 minus 2 pi, as we set out earlier. So 3 minus 2 pi minus 0 is going to be the case, waiting for us at x is equal to 0. Then at g of 7, okay, looks like we have our... and we got that one cut off first, so that's going to be f of 7 minus a 7 at the end. Okay, so because of that, we then need to go ahead and start solving for that, given that f of 7, right, in itself is going to be that change in the, again, in that function, in the function right here, right? For this, I think it'll be a bit easier if we just did that starting from 4 to 7. Yeah, so from 4 to 7, this point will be a lot easier for us to then find the area underneath that curve, because we don't have to include that semicircle. So f of 7, do another backtrack as if it was part A. Again, this is going to be from the interval from 4 to 7, f prime of x dx. Okay, but again, in that case, we still need to add the f of 4, which we know earlier from the start of the problem, off to the side as well. Okay, so because of that, from 4 to 7, this interval is going to be, if we really wanted to show it, it will be basically a triangle and a trapezoid right there. Again, going from 4, as you can see it, right? So 4 is this larger triangle listed right there. And then going from 6 to 7 is going to be a trapezoid of 2 separate heights going across there. Okay, so f of 7 is going to be, in terms of the integral, is going to be that triangle coming across, to and raising up to right there from 4 to 6 and from 0 to 2. So because that's 1/2, a base of 2 and a height of 2, added with the trapezoid here with a base of 1, height of 1, and height of 2 right there. So trapezoidal, very simple, for we calculated that for Riemann sums. So height of 2, height of 1, and we take the average of the 2. Okay, and the 1/2 is there. It should be plus multiplied by another 1 as the base. Okay, and lastly, adding the f of 4 at the end, which is a positive 3 given to us at the start of the problem, is the way that we can then solve for f of 7 quite nicely. So by doing that, 1/2 of 2 times 2 is going to be positive 2. This is going to be 3 over 2, so plus 3 over 2 as the trapezoid, and lastly a plus 3 at the end. Adding all that up together will be a whole 5 and a 3 over 2. If we really want to leave it as a mixed number for now, that's going to be 6.5 as a result of all that addition. So we can leave that there. That's a pretty strong candidate, but we'll see what that looks like at the end. As lastly, f of 5, we've already found. My pen is running out of ink, so real quick. So f of 5 that we found earlier at the start of part A, that we've already done, the work is going to be a nice 3 and 1/2. Okay. So whole 3 and a 1/2. So we just piggybacked a little bit off of our previous work in part A, but all of those are listed out. Of course, the absolute maximum is then going to show its head at 7. Okay, so f of 7 is, no, well, that f is, sorry, this is actually for the function of g, right? So instead, that actually lets us catch one little thing over here, is that we are looking for the function g. So actually, f of 7 minus a 7 is going to be the function of g of 7, which would be negative 1/2 as a result from that 6.5. And then the same thing happening here as the f of 5 So g of 5 is equal to f of 5 minus 5, giving us a negative 1 1/2 as a result. So that kind of throws things out of contention here. But even with that, with a 3 minus 2 pi, again, that's going to be less than the negative half. So it looks like everything is still in order here, that g of 7 is the maximum. We're not looking for maximum. What am I doing? We're looking for the minimum, which in this case, it really should be 3 minus 2 pi. That's really low, yeah. So the g of 0. Well, I'm really running out of space here, but nonetheless, g of 0 is the minimum. After all of our work is shown right there. Okay. So 3 minus 2 pi versus negative half versus the negative 1 1/2. So g of 0 is indeed going to be the case there. A little bit messy, but I think we should still be good for it. Again, all we have to do is really compare all 3 cases, remembering that we are doing the function of g, defined here earlier as g of x of f of x minus x. So g of 0 is going to be the minimum in this case after comparing all of them. Okay, very nice. So with that, we have everything we need to move on to question number 4, and we'll see how we are scoring after that. Okay, question number 4 is throwing at us a very lovely table. So t is in days, and then r prime of t is in the centimeters per day as a rate. So let's go across and see what that looks like for us. So we go from 0 to 3 to 7 to 10 to 12 days recorded out for us. So r prime of t is negative 6.1, negative 5.0, then negative 4.4, then negative 3.8, and then negative 3.5. Let's clean that up a little bit. So negative 3.8 right there. Okay, good. So we have that listed up for us. Then we have the context as follows. It says here that an ice sculpture melts in such a way that it can be modeled as a cone that maintains a conical shape. Okay, as it decreases in size. Okay. The radius of the base is given by a twice differentiable. Function r, where r of t is measured in centimeters and t in days. Okay. Yep. So we have everything listed out there already on the table for us. So let's see to what they are asking for us in the first place, and we'll have a look. So they want us to approximate our double prime of 8.5. Yep. Okay. Using average. Okay. Using average rate of change. They just tell us already. Using average rate of change. Okay. Of r prime over the interval 7 t to 10. Okay. And then show that work, and then units of measure needed as a note here for us. Okay, very good. So we got a lot of things going on here, so let's go over really quickly to make sure we're all on the same page. They gave us that table, in which they're measuring t in days for this ice sculpture, r prime of t, again, the rate at which it is then melting down, okay, across the interval from 0 to 12 days. And it remains in a cone shape for us as a point of reference to what this might look like if we are trying to measure that volume decrease over time. Okay, so because of that, let's go over to part A again. They want us to approximate our double prime of 8.5. They already threw us the bone that it's using average rate of change because of that. Okay, of course, again, is that we have the values of r prime of t. So if we did r prime, given that's 8.5, that's going to land in between 7 and 10. Those are the 2 points that we're going to use. So r prime of 10 minus r prime of 7 all over 10 minus 7. And this is how we set up for the average rate of change as a way to approximate for the next derivative on this function. Okay? So all this really is a nice simple plug in for us. So negative 3.8 minus a negative 4.4, keeping track of the negatives there, of 10 minus 7. Okay, so very easy for us to just work this along, understanding average rate of change and what that means for us. So because we're adding a 4.4 in essence over there on the numerator, it's going to give us a positive 0.6 divided by a whole 3, giving us 0.2. And in terms of the units, again, we're doing r prime, which is the centimeters per day, but we are also dividing it once more by days again, right, with that ratio set up there. So because of that's going to be the centimeters per day squared as a result of those units, right? So this is a change in the rate at which the sculpture is melting. Okay, very nice. Then going to part B, they're asking, is there a time t, again, in that interval from 0 to t to 3, for which the r prime of t is equal to negative 6. And they want us to show if we can guarantee that, right? Showing our uses of theorems of calculus for us to help us out here, right? They want to know r prime of t is equal to negative 6, and we know that negative 6 is going to be, should be somewhere in here. We just need to know exactly where. And of course, it does help to know that r is the function that is twice differentiable, right? So given that, again, so we know that given because r is differentiable, right, on the 0 to, for t going all the way to 12 again, that means that r is continuous on that exact interval going all the way to 12. Okay. So because of that, we have our work cut up for us, given that r being continuous over the interval that we're looking at for this entire function. Well, that means that we can go ahead and use, so we can actually prove that yes, r prime of t equals negative 6 does exist on the interval 0 to 3, again, that interval that I'm looking for. As you can see, if you look from 0 to 3, we are traveling from negative 6.1 to a negative 5.0, right? And because r is continuous, again, by the intermediate value theorem, so IVT, remember that we have a continuous function going from two separate values. That means that there has to be at least one point in between those two values that must exist for this continuity to stay in place, right? Okay, the r prime of t equals negative 6 is guaranteed to exist on the interval 0 to 3. Okay. And we've proven that, we've already shown that r is going to be continuous over the interval. So that carries over for us to then use intermediate value theorem to confirm that in our work. Very good. Okay. Then part C says that we must use a right Riemann sum. Okay. With 4 subintervals. Okay. Yep, to approximate now the 0 to 12 integral r prime of t dt. Okay, very straightforward for us. I like these kinds of problems with the right Riemann sum, meaning that we need to go and take the right side points. Let me switch colors again. Where's that? Where's my pen? Okay, Again, with 4 subintervals as shown in the problem, that means the heights of these equations are going to be the 4 right values as circled. Oh, you can't really see that very well. Let me swap colors. Man, I have to really work on finding the right colors. Maybe I have to refill my orange pen. But for now, we have a nice darker blue right here. This should stand out a little bit here. So we have those 4 values in which we are going to take the heights of them to find the Riemann sum on. Okay, so because of this, let's go ahead and put this through. Again, each of the bases are actually going to be very important to keep track in mind. Again, this is the simple base times height to find the area underneath that curve that we're looking at. So with the base of the first rectangle going from 0 to 3, the base of 3 multiplied by that right-hand height of negative 5.0. Adding with the next base going from 3 to 7 is going to be a base of 4 with a height of negative 4.4. The next height then going from 7 to 10, that is another base of 3 multiplied by that height of negative 3.8. And lastly, the base of 10 to 12, so a base of 2 going at negative 3.5 right there. Okay, so all of that looks like it is going to go through in place without a problem, and we just need to mathematically solve for it, that is, for these parts. So we get negative 15 keeping the signs intact here, so negative 4.4 times a 4 will be a negative 17.6. Okay, 3.8 and a 3, so negative 11.2, 4 that is, the 2 got carried over, 1.4, and then lastly 2 and a negative 3.5 is negative 7.0 as a result. Okay, very easily worked out without a problem. Then we just got to subtract them all out. It should be a negative value given all the heights were negative to begin with. So taking care of the tens place, 6, 4, and a 0 makes it 0 again. We just carry a 1 into the ones place. 7, 7, 1, 5, 14, 19, 20. Exactly, yeah, 20 exactly with the 1 carried over makes it 1. Carrying a 2, 1, 1, 1, 1, so 5. 50, negative 51.0 as a result. And this should be in just centimeters as we integrated for that amount. Okay, pretty simple. The math looks like it checks out quite nicely for us, even without a calculator. So let's move on to part D here. It says here that the height of the cone decreases at a rate of 2 centimeters per day. Okay, and then it then notes that at time is equal to 3 days, the radius is 100 centimeters and the height is 50 centimeters. Okay. Then it says to find the rate of change of the volume with respect to time in cubic centimeters per day. Okay, at the time is equal to 3 mark. Okay, and even though I personally wouldn't like it if they did, but they threw it at us anyways. They gave us a hint that the volume of a cone is 1/3 pi r squared h. Okay, again, volume of cone. They threw us that hint just because they were feeling nice. I personally would not have, but that's what they did for us so that we can easily find that out. Okay, so they gave us already the height of the cone decreasing at 2 centimeters per day as a rate. That is already a nice hint for us because that means that it's the dh over dt. Again, a rate of the change in height in respect to time. Again, that's a decreasing, so it's negative 2 centimeters per day to keep the units intact there. Okay, and then the radius is going to be 100 centimeters and the height is going to be 50 centimeters. Okay, at a given time. Again, this is going to be at the t is equal to 3 mark. Okay. We already know the change in the radius as well at time is equal to 3, as shown right there on the table. Maybe that could be helpful to us, as we can keep that in mind. So the rate and change of the radius at time is equal to 3, as given to us at the table, is negative 5.0 centimeters per day as well. Something maybe to keep track of that might help us along here. Who knows? But we'll find out. Okay. So we need to find the rate of change of the volume of the cone with respect to time for that guy. Okay. With us knowing that height and radius are changing in respect to time, this means that we have to do all of this implicitly. And this is implicit differentiation. Given that, again, the r in respect to time, again, this can be dr over dt, and the height derived in respect to time will also be dh over dt. Again, none of them will go to 0. We have exactly the rate changes on our side given to us quite easily. Okay, so with that, we then need to go realize that we have a volume equation at the 1/3 pi r squared h. Okay, but we don't care about the volume. We are caring about the change in volume in respect to time, and we need to derive all of that. Okay. Something, of course, in mind is that 1/3 pi is a coefficient, so we'll just simply leave that on the outside to be contended with later, while the r squared times h need to then be derived. So this is going to be a good use of product rule for ourselves in terms of the differentiation. So let's go about taking each of them and going with it. So exponent rule of the r squared will mean 2r comes down, but that also means that we have the dr over dt, again, derivative of r respect to time as a result of chain rule coming down. Cannot forget that. H will be left the same for now. And then we then go in the other side of h being derived after that fact with product rule, meaning that we leave r squared alone, and we end up with dh over dt being derived, waiting for us on that side. Okay, this is quite nice because everything from here can be very easily substituted in from everything that we've done so far. So the radius they gave us at the 100 centimeters at exactly that time is equal to 3 position. So we leave 100 centimeters right there. dr over dt is going to be the negative 2 centimeters per day. That's the height. That's negative 5, sorry, in terms of dr over dt, okay? And then h is going to be the height at that time at 50 centimeters, as was stated in the problem. So that's all going to be plugged in quite easily into that first part. And then radius squared, so that's going to be the 100 centimeters. Square that off. dh over dt, so the change in height in respect to time, that's a negative 2 centimeters per day. Okay. And all of this is exactly how you will plug in for this problem. Okay. So we have ourselves just a little bit of workarounds here, just to make sure we're all on the same page. We can do it quite nicely, actually, given the fact that 1/3 pi will be waiting for us at the outside of this. But we have a 2 times a 50 times another 100. So we can actually leave this in terms of 100 square centimeters, right? Or 100 centimeters, all that squared, right? So we can clear out the 2 and the 50 and the 100, as we have negative 5 centimeters per day as a coefficient of 100 centimeters squared. Why is that important? Of course, is that we already have another 100 centimeters squared waiting for us with multiplied by a negative 2 centimeters per day. Something very nicely, we can leave the coefficient there as then 2 centimeters per day multiplied by the same exact 100 centimeters squared. So before we have to be contending with a bunch of zeros, as 100 squared is going to be 10,000, we can do a nice little coefficient maneuvering here of negative 5 minus another 2. So with that 1/3 pi, it's going to be a negative 7 centimeters per day as a result of that, multiplied by 100 centimeters, all of that squared. So remember, we have to still square it at the end of the day here quite nicely. So that's 100 squared, that makes 10,000, and negative 7 makes it negative 70,000 divided by 3. So negative 70,000 divided by 3 multiplied by pi, and this can be centimeters cubed per day as the rate of change of the volume in respect to time as the volume of the sculpture that is being melted away every day. Not bad on that part, I wouldn't say, as that concludes problem number 4 for this packet. Okay, the math checks out. We plugged in, looks like everything quite well on this part, and we just have to put in through to see what our answers will look like. Okay. So let's go on back to question number 3 first to see how well we scored on that part, and we will get to question number 4 and tally up our totals on this second third of this exam. Okay. Question number 3, and starting with this lovely graph of the semicircle and the 2 lines right there. Putting that through, we were looking for the 2 points f of 0 and f of 5. We do need a setup for fundamental theorem as shown, again, of the 0 to 4 as shown right there, right? So they were looking for the setup of 0 to 4 f prime of x dx, right? So by doing that, we show that we have a negative coefficient. Yes, okay. I think that is one thing that we get dinged, unfortunately, already. That is unfortunate. I think that might carry over. That is very unfortunate that we've broken our streak of getting everything correct so far, because with this negative coefficient waiting for us, I really thought I carried that over with the negative, and no, because that's a negative, we need to have a negative on that side as we were underneath the curve at the time. Wow. Well, that's kind of sad, but nonetheless, though, it should have been 3 plus 2 pi. Okay, so us setting it up, though, was going to be 1 point, but the 7 over 2 was indeed correct for the f of 5 point. So, unfortunately, this just means that we get only 2 out of 3 correct for this part. Us missing that coefficient would be enough to, us missing that negative sign will be enough to have us lose a point. Very unfortunate that we weren't careful enough on that part. I really thought it was, but I guess not. Okay, then going over to part B here, we are looking to make sure that we have the point of inflection. Okay, so at x is equal to 2. What is happening? That's kind of sad. That was supposed to be at 2 because this is at the 1 and 2's position right there. So that is unfortunately another mistake done on my part. That was meant to be a 2 instead of x equal to 1. I really don't know why I put in 1 right there. But the idea still holds that this is meant to be the change as the increase to decrease for that first derivative. That reasoning was exactly correct. It's just unfortunate that I couldn't read my own tick marks of my own graph. So because of that, this would only mean that we get the right point on the justification. That's good. It's just that we had the wrong value, so that's going to be 1 out of 2 correct on this part. Very unfortunate. But nonetheless, though, that is good to show that we still understood what points of inflection were. It really was just a very unfortunate matter. Again, our reasoning was good. It's just we couldn't exactly read a tick mark on a graph. Okay. Going over to part C, we have that function described as such. So we take that first derivative of g going as f prime of x minus 1. That's exactly what they wanted to see for us understanding how to take that derivative to find the decreasing section of that. And the interval going from 0 to 5 for x was indeed going to be correct, as everything underneath the graph of f prime 1, again being less than 1, was the right way to display that relationship for that point. So all 2 out of 2 were going to be correct. Okay, for that part. And then lastly, let's get over to part D here. A little bit scrunched there, but the minimum must occur at x equal to 5. Yes, unfortunately, that's going to be incorrect, but we still showed that we were looking for the g prime of x being equal to 0. That's what we need to consider if we're going to do any sort of local minimums on our part to find the part of absolute minimums. So that's one point in which they're looking for us to confirm. It's just unfortunate that our answers, because of the way we forgot to put the plus 2 pi, 0 could not have been the absolute minimum, meaning that it was going to be x is equal to 5 to be the actual minimum. So it should have been g of 5 instead. That is no good, but that leaves us at 1 out of 2 correct for this part as well. Okay, so because we missed 1 on the first part, another 1 on the second part, and another 1 on the third part, that is only going to be 6 out of 9 points for this part. Very sad for us, because those are just very simple mistakes that carried over, which should have been very easily caught and followed up with. So another lesson for us to at least remember that we have to be as careful as we can on our parts to make sure we don't mess up something very simple like a coefficient, which will catastrophically demolish, as well as a reading of a tick mark to demolish the way our answers have been going. Okay? As something that should be stated here, and especially in practice, is that the inch could mean a mile for us in terms of the way things are being graded. Okay, but enough of that. Let's keep going with problem number 4. Again, our reasonings were all correct. It's just simply the way that we have to make sure our coefficients of pluses and minuses and reading of tick marks need to be on point. Nonetheless, though, let's get over to part A on problem number 4. So by doing the average rate of change that they asked for, setting up of the r double prime of r again as the average rate of change equation between 10 and 7 as the right points for us, and by running the equation of the 0.2 centimeters per day squared, right, again per day, the units were indeed going to be correct, as well as our supporting work of knowing how to do the average rate of change. So this is going to be 2 out of 2 correct for this problem. Very nice. Okay. Then going to part B, they were looking for the time at which it's going to be guaranteed that the first derivative of r is going to be equal to -6, right? And because we did prove that the actual function of r was continuous because it was differentiable over that entire interval from 0 to 12, right? We then did show that the IVT can be used by intermediate volume theorem to show that we're going in between -6 to -6.1 to -5.0, meaning we are guaranteed to cross -6 at a certain point on that line. So therefore, we've proven that that was going to be the case to prove that r prime of t being -6 was going to be correct. So 2 out of 2 have been scored quite nicely. Okay, then going with the right Riemann sum approximation, right? By doing that form again, yeah, we did show all of the work that was needed. Again, each base multiplied by its corresponding height: 3 and -5, 4 and -4.4, 3 and -3.8, 2 and -3.5. Okay, all that really remained is that understanding that we had to take the right-sided heights that we were given so far and keeping track of each base going across the 2x values to make up the base of each of the rectangles that we're adding up, giving us a total of -51 as was needed. So that is 2 out of 2 correct again on that part. Okay. Lastly, let's go over part D, where we're doing the rate of change for the volume of the ice sculpture as a cone. So yes, we do need to show that we are using product rule to have dr over dt and dh over dt shown as each of them were, again, taking the derivative of on terms of r and also in terms of h, because that was one point that they wanted to show, as well as chain rule of understanding how 2r and dr over dt was going to be shown as a result there as well. Okay, so with the arithmetic being exactly correct the way that it should be, we end up with the volume change of -70,000 pi over 3 as shown. Again, this is going to be centimeters cubed per day. So all 3 of those were correct as a way to show for this part of the exam. Okay, so it looks like we have redeemed ourselves a little bit, not missing a beat on question number 4. So we go back to 9 over 9 on there as well. Okay, very nice. So let's see if we can finish strong here on questions 5 and 6 for us to follow that up exactly. Okay, and it looks like actually that on problem number 5, I need to do the first part of the problem on the paper, as we have ourselves, as you can see, a slope field on this portion of the problem. Okay, so let's get back over to it and let's have a look here. Okay, let's read it out first and then we'll get to it. Actually, you know what? Let me first copy it down because the rest of the problems will be on the notebook. It's just that the slope field question has to be answered on that packet. So at question number 5, we have the differential equation. Is this pen really? Come on now. Just gotta refill that really quickly. So dy over dx differential equation is equal to 1/2 multiplied by the sine of pi over 2 times x. Okay, multiplied by the square root of y plus 7. Very nice. Okay, so they'll say let y be equal to f of x. Okay, and we have the solution f of 1 is equal to 2 as a point. Okay, very good. All right, So all of that is set up right there, but question A will be done on the packet. Okay. So in this case, we have the slope field right there. Again, you see all the nice lovely tick marks there for the differential equation that they have described there at the top of the problem. Okay, but they wanted to show this, we wanted to sketch the solution curve going to the point 1, 2, again to show that we understand how to draw potential solutions to a curve using the slope field. Okay, this should be fairly straightforward because going through the point there means that we just simply follow everything moving across. So we will go to an increase, and then we straighten out to a 0 slope right there at that point right there, and then we need to get down to a decreasing slope moving all the way down on that side. Okay, then we need to follow along with the other part of this slope field. So we will then decrease on this side, we straighten out at 0 at that point, and then we increase once more. Okay, and then we straighten out at another 0 right there, and then we decrease after the fact into more negatives on that side. Okay, so this is going to be one potential slope field solution that can be given, that we cross through the point that they asked for, and that really is it. Right? They're pretty loose on this grading because it's just a sketch of a potential solution. It's not really something that they're going to look too deeply upon unless it's something egregious against the problem. Okay, well, other than that, we'll get back to it once we start grading it. Should be very simple. Again, you're really just following the tick lines in terms of these possible slopes that you cross through. So with that, let's go over to part B. Okay, the part B is asking for us to write an equation for the line tangent, to the solution curve in part A, okay, at the point 1, 2. Okay. And then also then it says to use the equation to approximate f of 0.8. Okay, very nice descriptions for us right here. So again, we need to do a tangent line equation, right? Again, at the point 1, 2, and then we'll do an approximation of a point next to that. Okay, tangent line equation obviously means that we need to write the equation of y is equal to the slope of x minus h plus k on the outside. Thankfully, they gave us a point 1, 2, so again, that's h, k for us in the point slope form, meaning that all that we really need left to solve for is going to be the slope of m, right? M given where? Again, m at that point 1, 2 for that differential equation that they gave us. Again, evaluate at 1, 2 as they asked us to do at the start of the problem. Okay, so we just need to do a very simple plugging in here in terms of the x and y points right there in the variables for us to then find that slope at that given point. So plugging in 1 for the x where it should have been in the part of the problem, and then 2 in the y where it should have been in the y spot on this, right? Both x and y are contributing to the slope here for this type of problem. So with that, we can go ahead and solve for the slope here. Sine of pi over 2, so sine of pi over 2, again, this entire guy is going to be a positive 1, thanks to some unit circle recollection. And then the root of 2 plus 7 is the square root of 9, meaning that we have 3 over 2 as the slope of that line. So we plug everything here as y is equal to the slope of 3 over 2 multiplied by x minus 1 plus 2 on the outside. Okay, very nice for us. And so with that, we can go right on ahead and go boxes as the first part of our answer, and then we need to go for f of 0.8 as an approximation. So with that, we go 3 over 2, plug in the 0.8 on the x, subtracted by the 1 on the outside. Let's make sure all that's within the slope right there. So this is negative 0.2. Negative 0.2 in our case, if I want to leave everything in terms of fractions for peace of mind on our side, that means it's going to be negative 2 over 10, so negative 1 over 5 as a result of that fraction there. Okay, So that's going to be 3 over 2 multiplied by negative 1 over 5 plus 2 on the outside, giving us the negative 3 over 10. Negative 3 over 10, thankfully, is going to be the negative 0.3. That takes so long to remember. So we can approximate f of 0.8 being approximated to the positive 1.7. 1.7, that's right. Okay. Just a little bit of fraction and decimal practice right there, but very easily we have our approximation, both parts in which they were asking for. Okay. Then for part C, it's saying that it is known that the second derivative f double prime of x is greater than 0 for the interval of negative 1 to positive 1. Okay, so they're asking, is the approximation on part B an overestimate or an underestimate for f of 0.8. Okay, so very simply put, again, doing over and under approximation evaluations for this type of function. This means we need to understand the two things that are happening, right? For one, f prime of 1 for us that we've shown in our slope right there, again, was we approximated at 3.3 over 2, meaning that it's positive, meaning that it is an increasing, right? And given that f double prime of 0 is going to be the x, that is, at the 1 part is equal to greater than 0. It's also positive, right? So this accounts for 1 as well, given that it was part of that interval that they provided to us. So given that's positive, we are concave up as well with that second derivative, right? Increasing and concave up. What that looked like, right? If we had a very simple idea here, we're concave upwards or curling upwards with our function, right? And we're increasing, again, we're increasing up on those y values. So what would that look like if we were to then take a tangent line that is just a linear part, right? And our function goes on its own, right? As you can clearly see, a little bit exaggerated here, but the idea is still the same. That if you're increasing and concave up on an approximation that is linear, you will be doing an under approximation, right? Approximation of f of 0.8, right? Given all the details that we've shown of an increasing and concave up function, in reality, well, if we go on a straight line tangent and keep going on its linear way, it will end up underneath the actual function itself. Okay. Then lastly, in part D, it says here that we want to use separation of variables to find y is equal to f of x. Okay, and then the with initial condition of the f of 1 being equal to 2. Okay, so we have ourselves our work cut out for us once more. We're doing a separation of variables to find a particular solution to this type of integral. Okay, so along with that, we have to start with the dy over dx being equal to the 1/2 sine pi over 2x multiplied by the square root of y plus 7. Yeah. So separation of variables will mean that yes, indeed, we have to start moving everything in terms of the y's over to its side on dy, and then dx moving everything over to its side with the x's. So with that, we end up with dy over the square root of y plus 7 being divided on one side with the 1/2 times the sine of pi over 2x multiplied by dx waiting for it on the other side. Okay. Very nice. That just means that we have to then integrate for both sides of the equation, as this is how we do our separation of variables. It's integral of 1/2 sine of pi over 2x times dx. Yeah. So with that, we have ourselves the actual integration that can follow. Square root of y plus 7 on the denominator will then mean that we have to bring this back up as y plus 7 raised to the 1/2 power, us keeping the positive 2 as a coefficient. Again, we're keeping in track with the 1/2 that will come down as a result. And then we have on the other side a positive sign, meaning that we have to go negative 1/2 times a positive cosine of pi over 2x. But then, because we have the pi over 2 waiting for us as a coefficient, we need to multiply by its reciprocal 2 times pi waiting for it, as the chain rule will follow accordingly. And then a plus c, as we are doing indefinite integrals. That's something that's very important for us, that they will ding you plenty of points for if you do not leave the plus c at the end of that. Okay, let's do a little bit of cleanup here. The negative 1/2 with the 2 up there. Okay, and then we can then solve using the initial condition of 1 comma 2 as something that we can use to then isolate plus c on. Okay, so let's go ahead and plug that in over on this side. So it's 2 multiplied by a 2 plus 7 raised to the 1/2 power, being equal to negative 1 over pi. That's what the reduced coefficients will look like from that result on the right side of cosine of pi over 2. X in this case is plugged in as 1. Okay, and then plus c. Okay. That will still be waited for us to solve for. Thankfully, cosine of pi over 2, that's going to be 0, meaning that the entirety of this guy will all go to 0 in this base case, which is very nice for us. 2 plus 7 to the 1/2 power means that 2 times 3 as a result, being equal to c being left alone there on that side, making c being equal to a positive 6. Okay, so with that, we have almost everything done here. We just have to do a little more isolation here. So the negative 1/2 actually should be negative the cosine of pi over 2 times x all over pi as its coefficient, plus a 6 waiting for us on that side. Okay, so all of this is ready for us. We just need to then isolate the y on its side. So then we just move over that 2. So y plus 7 to the 1/2 power is equal to negative cosine of pi over 2 times x all over 2 pi plus 3 with some distributive property, the 2 being divided everything on both sides right there. And then to cap everything off, we end up with y being by itself. Again, squaring first and then subtracting 7 on the second step there, which means we have all of negative cosine of pi over 2x all over 2 pi plus 3. All of this needs to be squared first, and then we move that 7 over through subtraction. Again, order of operations really does matter, and we end up with this, again, this being f of x. That's what they called y being equal to. Finally isolated and singled out as a pure result of this integration. Okay, quite a few lines of work, but this is definitely something that I can definitely see being asked this year as another sense of doing separation of variables and all the integral rules being followed for things like sine and square root in the denominator. Everything seems quite nice, at least for us here. So that will conclude it for question number 5, and let's get on with the last question of the exam. Okay. So with question number 6, this will be the end of the 2022 exam, and we'll see how well we scored according to that. Okay, so it says here that particle P moves along the x-axis. Okay, such that for time t is greater than 0, its position is given by x of p of t being equal to 6 minus 4 e raised to the negative t. Okay, then it says here on the next part that particle q, okay, moves along the y-axis. Okay, such that for the time p is also greater than 0, its velocity is given by v of q of t being equal to 1 over t squared. Okay, and then at time t is equal to 1, let's see, it says here that the position of particle q is x of q of 1 being equal to 2. Okay, so we got a lot of things going on here with two different particles moving in two different directions. What a joy that is. But nonetheless, though, let's get over to part A here. It says that we want to find v of p of t, again, the velocity of particle p at t time. Okay, so the to know, of course, is that we have the position of p with that equation, and then we have the velocity of q with that equation. Again, both of them are two different things. Now they're asking for the velocity of p. Of course, with us understanding that velocity is simply going to be the position graph, the one that they gave us earlier for that particle, with its derivative respect to time taken one time. Okay, so with that, we're then going to take the entirety of 6 minus 4e to the negative t power. Again, take that guy's derivative. And so we just simply have to follow a nice exponential rule here, with the negative t coming down as a -1 coefficient, and coming down as a -1 coefficient for us. So because of that, and the 6 going to 0, that will just mean that we end up with the velocity of p in respect to time is going to be a positive 4e raised to the negative t power. Very simple, meant to be very easy, but they are confusing us a lot with the context early. Nonetheless, though, let's go over to part B here, that we want to find a of q of t, right? The acceleration of particle q at time t. Okay. Yes. And we have a lovely message from Mijin Yang that we are back here again. Indeed, we are. Yes, we're almost done here with the 2022 free response question packet. And hopefully with this being well recorded, that we can have our results viewed by our loyal viewers once we are through here. But we are going through these last problems here, and we'll see to it what we end up with at the end. Okay. So with that acceleration waiting for us right there, okay, then it will continue that we need to find all times of t for t being greater than 0 when the speed of q is decreasing. Okay, we've got a lot of things going on here. Mijin is asking, can we write a little big? Yes, I believe I'm writing as big as I can, but maybe we can write even bigger if that's something that's needed. I know on the phone it might not look as clear, so we'll keep that in mind if we keep going. Pages should not be any big issue on this side. Okay, but nonetheless, though, we need to find the acceleration of the particle q. Okay, which in this case, again, that first part means that we have to go take the velocity vq of t and take that guy's derivative, again, as that is going to be the actual relationship between velocity and acceleration, right? So that's how you find the acceleration of q in respect to time. Yes, Mijin is saying it's hard to read. Yes, I will definitely keep that in mind as we move along here. Yes, thank you for your feedback on that. Definitely writing clear is going to be very important for the viewers in the first place. But nonetheless, though, we have all of this set up here, right? So we first need to take that first derivative of v in respect to time. But also, if they want to see that the speed is decreasing again, to show that we're on speed decreasing, right? This is going to be important, as speed decreasing is going to be the relationship that the velocity in respect to time and the acceleration in respect to time, again, have different signs, right? So in this case, right, either the velocity is going to be positive and the acceleration of that same particle is going to be negative, or in the other sense, the velocity of that is going to be negative and the acceleration of the same particle is then going to be positive, right? We're looking for different signs on this particle such that we can show that the speed is decreasing, right? That is how we can go ahead and determine that in that sense. So we still have our work to do here for the first derivative of velocity. So let's go ahead. Again, this is velocity of q, meaning that we have to go ahead and take the velocity of q respect to time. Its derivative is going to be the 1 over t to the second power, and take this guy's derivative for us to get into the acceleration. Okay. So because of that, taking the derivative of 1 over t squared, this is going to be the, you can think of it as t to the negative 2 power in that sense, meaning we have to bring negative 2 down as a coefficient, and it'll be t to the negative 3 power, which in our case is going to be negative 2 over t to the third power, and this will be the acceleration of q respect to time. Okay. This is the first part of the question that they were asking for, and now we need to get over to the next part, which is going to be then showing that the velocity and acceleration of that particle q are going to be different, right, for all times in which it is greater than 0. Okay, so because of that, we need to go see that, for one, is that with the acceleration, right, something we have to take a note that aq of t, right, is always negative, right, when the time is greater than 0. Of course, showing that we have a negative coefficient waiting there on the acceleration, and with t raised to the third power, right, all of those values will then result in the entire acceleration always being negative. If that's the case, we need to know where the velocity is positive for this to counteract and to conclude that the particle is slowing down, right? So with the positive then from 1 over t squared, right, as you can see here, with 1 over t squared being the velocity, right, it will be always positive, and we can now enter in that it's always positive, because 1 over t squared will result in all positive numbers, although they might be small, but it's for all of t being greater than 0. So therefore, right, the particle q is slowing down when t is greater than 0. That entire time, because we have mathematically shown that the acceleration will always be negative and then the velocity will always be positive, given the two relationships of those two, we then can conclude that it will always be slowing down because of it. Okay. Very nice. Then let's go over to part C here. Let me double check here if we're good on that. Let's go ahead and rewind that just to make sure we're good on that playlist. Okay, very good. All right. Yes, Mijin says that she can see well now. That's very good that our viewers can definitely see the writing that we have here. Okay, then for part C, it says that they want to find yq of t. Yes, yq of t. Yep, yq of t. Okay, the position of particle q at t time. Okay, so now we need to take a step back here of the actual position of particle q, meaning that if we want to find yq of t, this is going to be in relation with the indefinite integral of the velocity of t. Again, we need to take a step backwards in terms of that particle q with its velocity. So by doing that, we also still have, and we need to take a note here, that we do have the actual original position of xq of 1 being equal to 2. That should have been y. I copied that wrong because this is going to be on the y-axis. Right, so that is applicable to this problem, right? With that, the y of q of 1. So again, we have 1 point on that position graph that we already know that the question gave to us, which will be something very important to keep in mind as we move to solving this problem. Okay, so an indefinite integral of the velocity function will then be 1 over t squared dt. Remember, we are now taking an integral, not a derivative like the previous problem, meaning that we need to take a step backwards as the t to the -1 power, again moving that integral and moving that exponent back a spot, but we still have a negative coefficient to contend with because of that negative exponent there, plus c because we are doing an indefinite integral. And so with that, this is going to be one form of the position of the particle q, but that means we need to solve for that c because they want to know the entire function in respect to time. So by plugging in the 1 and the 2, 1 in terms of t and 2 in terms of the actual position, we then get the negative positive 1 to the -1 power plus c being equal to positive 2. Okay, so as a result of that, 1 to the -1 power, thankfully, is going to keep us at a positive 1, but that negative will end up with a -1 waiting there for us, and so the actual value of c is going to be 3 as the constant of integration. So because of that, we can then finally plug that back in to our original position equation of yq of t being -1 over t, just to clear up that -1 exponent, and to throw that into the denominator, plus 3 on the outside, and that will be the answer to question C. Very nice. Okay, so let's finish this off with question D, and we get to see what our total will look like at the end of our session here today. So it says here that as t approaches infinity, which particle will eventually be farther from the origin. Okay, and we need to give the reason. All right, this is actually the first time I've seen anything like this, but this is definitely still a calculus problem. Just haven't seen this yet on a practice part, because as a note here, again, we want to note that infinity is not a number, right? So it will be bad math for us, right? We cannot call that, oh, hey, let's just go, we put the positions x of q of infinity and we'll see what that is incorrect. We cannot plug in infinity into an equation because infinity is not a number, okay? The best way for us to show what the actual trend will be like for these particles as we go to a very large time frame here is that we then have to take the limit as the time goes to infinity for each of these guys. So that's going to be x of the particle p respect to time, and the same thing was the limit as t approaches infinity for the y value of q of t. Okay, so because these are one-dimensional particles, very nice for us just to see what those actual numbers look like. So we can then plug that in. Again, this is going to be the limit as t approaches infinity of the first position of the p particle, so 6 minus 4 e raised to the -t power, and then for the other particle, particle q, which we just found in the previous problem, is -1 over t plus 3. Okay, so with that, if we evaluate this as t approaches infinity, as we just simply keep waiting to see what it turns out to be, right? So it's 6 minus 4 e raised to the -infinite power. Again, any sort of number raised to the -infinity power, meaning that we have the denominator, so this shows that, right? This is -4 over e to the infinity power. That negative is very important to keep track of. All of this will go to basically 0 in terms of a limit evaluation because you have extremely large denominators, in essence removing the entirety of the numerator. So because of that, we can evaluate the particle of p at the distance of 6, while on the other hand, with the -1 over infinity plus 3, again, this entire guy, because the denominator is extraordinarily large, this guy will then go to 0, meaning that 3 will be evaluated for particle q. Okay, so with that, we can very easily make our determination that particle p is farther from the origin. As t approaches infinity for this guy. That's meant to be fairly straightforward. Again, a little bit of understanding how to use infinities in terms of finding the ending trend of any given function using a nice limit. Okay, and that should do it for question number 6. So we have everything we need to move on back to question number 5, and that's correct here. Something to note again is that question number 5 to begin with was done on the packet, as we had to trace in a possible solution. Again, this is my handwriting with that lovely curve right there. So why don't we actually go ahead and swap back over to the actual computer screen here so that we can see what that looks like. Okay, so something to note is that with question A, and this is how they do the grading on the 2022 graph, is that again they show one possible solution. Again, we are curving, again keeping with the 0 tangents, again at those 3 points, so at the -2, 0, and +2. This curve goes up and down and crosses through that given point that they have right there. And then, okay, so if we actually go back over to what we had here, again, that's more or less exactly what we have. We have the zeros, again, something that to keep track of that I intentionally did, is that those 0 tangents at those given points was something that we had to keep note of as the function increased into a decrease as we curled around each of those slope field points. So for that, question A, part A for that is going to be 1 out of 1 correct, as we definitely saw on both of those. Okay, so pretty simple. On question 5, again, that was me. I would say as you just simply follow the slope field lines. Nothing too hard on that one. Okay, but going on to part B, and we're doing the line tangent equation for the differential equation, the dy over dx that they gave us at the start of the problem. So by doing that, yes, we indeed had to plug in for 1, 2 into the actual differential equation, giving us the actual perfect line of the 3 over 2 x minus 1 plus 2 on the outside. That's exactly what they wanted to see as the tangent line equation. And then for us approximating 0.8, we just have to plug that right into the equation of on the x value of that, and our approximation ends at 1.7. Both of them were exactly what they were looking for here, so that's 2 out of 2 correct for this problem. Okay, so both of them of understanding how to do the tangent line equation and the approximation at a given point are going to be tested right there. Then going for part C is that we know that the second derivative is greater. That was a very big hint for us. So with that, we were going to see if we were going to go as an over or under estimate for this type of approximation, right? So again, because we've proven that we are increasing and we were concave up, again, this is concave up shown in the little mock graph that I made for myself. Again, with any sort of tangent line coming across in a straight line, they were all going to be under approximations with those points being made right there. Okay, so because of that, we indeed proved that it is an under approximation, knowing that it was increasing and concave up. So with that, that will be just 1 out of 1 correct for part C. Okay, lastly, part D is where the really big stuff happens, because this is where we do our actual separation of variables integration for this part, meaning that again we had to move the y's over to the parts where dy was going to be, and we move the dx over to the right side because that's where the x variables were waiting on that side, right? The separation of variables is something, then we have to run the actual integration of both sides of the equation, not just one, right? And because of that, both sides of the equation, we end up with the negative 1 over pi, again, by getting rid of that coefficient. Again, the negative 1 over pi was indeed showing as the right coefficient there underneath the cosine, okay? And then the pi over 2x waiting for us with that plus c, very important to keep that in mind on the right side, while on the left side is 2 times y plus 7 all inside of a square root, or the 1/2 power. Either would work, those are correct. So both sides of the actual integration. Okay, then going on is that we actually then need to solve for the constant of integration, that's c, that we worked on through, meaning that by concluding that c is equal to 6, right, using the initial condition of what they gave us, f of 1 being equal to 2. Again, we plug that back into the equation, ending with c equals 6 at the end of our line of work there. Then, by moving everything over into the y as they wanted, y being isolated, being the 3, again, inside of the negative cosine pi over 2x with a -2 over pi coefficient. Again, all that matches up with the answer with a -7 weighting on the outside with the correct order of operations to show for it. So that is indeed going to be all correct all the way down the line. So therefore, we get 5 out of 5 correct all the way down for this problem. Very nice. Okay. Always remember that you will lose plus c is extraordinarily important for any sort of indefinite integral, while again solving for the c afterwards with the initial point is how you score everything you need to on this part of the exam. Very good. So looks like question number 5 will be 9 out of 9 correct there. So let's go ahead and take a note on that in our current grade with 9 out of 9. So let's see if we indeed can finish strong. Again, we did miss some points on question number 3, but with question number 6 being the last question here, hopefully we can end up with something of a nicer score than if we made those mistakes early. Okay, so with question number 6 over here, okay, those were the two particles here. Okay, so the velocity question again was just first derivative of the original position graph that they gave us at the start. So by running it, we get a positive 4e raised to the negative t power. That's exactly what they wanted to see. So that's going to be 1 out of 1 correct for us there. Okay. Very simple, very straightforward. Should not have been a problem for anyone else. Then moving on to part B here is that by then moving on to the acceleration of particle q that they wanted to find, we then had to take the first derivative of the velocity of q in respect to time to find that acceleration, which gives us that the -2 over t to the third power in the denominator. That's exactly what they wanted to see in terms of the acceleration. So that will give us a point right there. Okay. Then going forth, right, by considering the signs that, again, a of t will always be negative given that negative coefficient and t being always greater than 0. That was going to be the case for the acceleration. And the velocity always being positive because of the way that the velocity was set up earlier, again, with the 1 over t squared and t always being greater than 0, that would then justify for us, after that work there, that the particle q will always have a slowing down situation because the acceleration and velocity signs were always different from each other. So with that, that will be all 3 out of 3 correct for us. Again, understanding how to do the first derivative and a speed up, slow down analysis of looking at the positive negative sign for the acceleration and velocity equations. Okay. For part C, it was going to then ask us to find the position equation for particle q, meaning that yes, we had to go and take our integral of position to get the position, we had to take the integral of the velocity of q as shown in our work right there. Okay, so by doing that, again, we just run the integral, keeping up with that plus c that we had to solve with the initial condition. So by doing that, we end up with the -1 over t plus 3 on the outside. So again, both that, the integral, and solving for the initial condition in order for us to get an absolute and distinct equation were all that they wanted to see for this part, giving us all 3 points that were available for finding that equation. Okay. Lastly, over to part D, which was a little bit of the limit understanding. Again, as t approached infinity, remember t is but infinity not being a number, you can't simply plug it into an equation. You had to run the limits, right, of actually going to infinity. Again, infinity not being a number, you can't plug that directly into the equation. So because of that, they wanted to show and have it seen to them that we are taking limits as t approach infinity to see what the end behavior will be like for each of those guys. And by doing that, we end up with particle p being 6 units away while particle q is only 3 units away. We then can conclude that particle p is going to be farther away from the origin as we go to an infinite time frame. So with that, all 2 points are going to be correct to both show the limit and our conclusion. So because of that, looks like we got everything correct here as well, with 9 out of 9 correct for question number 6, meaning that at the end here, we have 9 out of 9 for question number 6. So with everything else being completely correct except for question number 3, we get 51 out of 54 points on this exam. Okay, so as just a little bit, if we want to see what that looks like percentage-wise, we can swap over to our trusty little calculator here. So with 51 over 54, and going by 100. Again, we end up with a percentage of 94.44%. Okay? Not too bad, at least for something that we could have very easily gotten 100 on because of some issues that we had with counting tick marks and keeping watch of certain signs on equations. So other than some very easy mistakes which could have been easily solved for, I'd say this is a pretty nice score, again keeping track of all the harder questions which we very easily answered across the board. Okay, so I think with that, that should just about do it. Okay, this will do it for the books for this 2022 AP exam. We only have so many more to go over as the exam itself is coming within the next month. So at least in terms of some channel updates, that yeah, we'll be looking at some actual ways to do some better YouTube full-length videos that I'm currently working on. Again, it will take some time as we're looking to compile everything that we've learned so far. But nonetheless, though, this entire walkthrough will be done and recorded on the main YouTube channel. So I think with that, that should about conclude for today's session. Again, any sort of emails or questions can be sent over to labcoatmath@gmail.com. But other than that, this should do it for about this one. Again, I do understand that many people do watch this as a recorded VOD at a later time. So all that will be available for anyone else to be walking through these questions for anyone else to see in the future. So I hope this does help for our students coming up on that exam. And we shall see you again next week, Tuesday. We'll be back here again at 4 p.m. Pacific to do these problems once more. So thank you all for tuning in to the 10th live stream, and we'll be going on to the 11th next time. And thank you all for watching, and we'll hope to see you again on the next one. Yes, thank you, Mijin, of course. Thank you for coming in and being as supportive as you usually are. We'll be back again on Tuesday, and we'll see you all then.